Complex zeros of polynomial functions. It says information is given about a polynomial function f of x whose coefficients are real numbers. The directions are to find the remaining zeros of f. We're given that this function is of degree 5. There are 3 zeros that are given, the number 1, I, and 2i. Because this is in degree 5, we know that there are 5 solutions. We could write the factored form this way, where r sub 1 stands for the first solution, r sub 2 is the second solution, etc. We know that irrational roots come in pairs and complex roots also come in pairs. If a plus bi is a root, then its conjugate a minus bi is also a root. So now the zeros of this function, we're looking for 5 zeros. The number 1 is a 0. Also 0 plus I, therefore 0 minus I. 0 plus 2i, and 0 minus 2i. Those are the 5 solutions. We have solved this problem. We'll go on to the next one. This particular function is of degree 6, and 4 of the zeros are given. We remember that complex roots do come in pairs, so we'll remember about the conjugates to include those among the roots. Since the degree is 6, we're expecting 6 zeros. There are 2 real zeros. There must be 4 complex zeros. If 2 plus I is a 0, so then is 2 minus I. Negative 3 minus I is a 0. Also negative 3 plus I is a 0. I've solved this problem. Now we're going to apply our knowledge of finding zeros to actually write a polynomial function. This problem is more time-consuming. Form a polynomial function f of x with real coefficients having the given degree and zeros. The degree that's given is 5. There are 3 zeros that are given, one of which is real, the other 2 are complex. We can write this in factored form this way. Our job is to find all of the roots or all of the zeros and then multiply them together. Remembering if a plus bi is a root, so then is a minus bi also a root. There are 5 zeros. We will denote them as r sub 1 is the real 0 of negative 2. R sub 2 is negative I, therefore positive I is also a root. R sub 4 is 1 plus I, therefore 1 minus I is also a root. I'm going to take these solutions, or these roots, and substitute them in place of the r's up above in the factored form. And I want to be careful with my signs and try to write this in a more convenient format. So instead of x minus negative 2, we'll write x plus 2 times x plus I. And then in those last 2 factored form, distribute the minus sign to both terms. Now what we're looking for is what can be multiplied that looks convenient. I'm looking at this x plus I times x minus I. And this is reminding me of the, when I multiply it out, it'll be the difference of perfect squares. And now the I squared, I know, is another name for the number negative 1. So I can rewrite this function. Now I've boiled it down to the, instead of the product of 5 polynomials, I have the product of 4. Let's take a look at the first 2 binomial factors and multiply those together using a box. X plus 2 goes along the top, and x squared plus 1 goes along the side. And we'll notice there's no like terms, so this one can be represented as x cubed plus 2x squared plus x plus 2. And now those last 2 factors, they look like they'd be more convenient to multiply together. So I'll multiply the 2 trinomials together. And they look like they're in the same form. It's an x and then a number and then the imaginary number. So I'll write x minus 1 minus I along the top. x minus 1 plus I along the side. And as long as I'm careful here, then when I go to look along the diagonals, I'm going to expect like terms. So I can rewrite this product as x squared minus 2x plus 1 minus I squared, or x squared minus 2x plus 1 minus a negative 1. And what started off as the product of 5 factors, I've now broken down into the product of 2 factors. So notice I have to keep going. I'm getting there, but remember the problem that was given looked like this. We found our zeros, remember, and this is the way the problem had gone. Now we have to multiply a 4-term polynomial by a trinomial. So let's put x cubed plus 2x squared plus x plus 2 along the top, x squared minus 2x plus 2 along the side. And we'll be careful. We don't want to do all this good work just to make a careless error here. We'll see if there's any like terms along the diagonals. And now we will finally represent our function, which we knew was a 5th degree polynomial function, as x to the 5th minus x to the 3rd plus 4x squared minus 2x plus 4. And so what I know before I even type this into Desmos is, according to end behavior, my right end is going to go up, because on an odd function, if the leading coefficient is positive, my right end goes up. Therefore, my left end goes down. There is a real 0 at negative 2, so I expect this curve to cross the x-axis at negative 2. There is a y-intercept of 4. So now I will plot this graph, and I will verify that y-intercept is definitely 4, and the real 0 is definitely negative 2.